Okay, so is this thing on? Yeah, okay, perfect. So I have a lot of slides, so let me get right into the meat of it. So the topic is, okay, actually using Kubernetes to solve persistent workload problems, and then the DevOps styles, because I want to talk a little bit about the CI/CD stuff around that. So quickly about me, as already said, my name is Jeffrey. I've been in storage for long. I'm starting to feel a little bit old. So I work for the company MyData, which sponsors the OpenEBS project. And to give you a little bit of a feel of what our vision is around data management, just real quick. So the idea is that if you have different persistent workloads across different systems around the globe, what we create is this declarative data plane around that. It actually allows you to move your data around. And we actually do the plumbing, and that was what we're talking about yesterday, is actually allowing you to do that. And on top of that, we extract a lot of information, some rudimentary stuff about performance and these type of things. And around that, we try to create additional things that help you manage these workloads, like preemptive moving the data and things like that. So with that said, a little bit of history. I think you guys already probably know this a lot better than I do, but Kubernetes was originally developed by Google, and if you haven't read the work paper, I recommend you do that. But it was mostly stateless applications. That is, if you believe there is such a thing, I think there's always a state. I think it's more accurate to say that you might not care about that particular state. But its most simplistic form, what Kubernetes does is it tries to converge to your desired state, which you impose on it through YAML and configuration files and what have you. But the key thing here is that the goal was to abstract away the underlying infrastructure such that the developers could focus on deploying the application, right? That was the real goal, and probably the most important. Oh, and by the way, avoid lock-in, which is a good thing to have. So if you look at the paper, you'll see this picture, and it kind of looks, what we have today. Some small, minute differences, perhaps. So here they're still using Paxos today. That's Raft, which is a more simplified version of Paxos, or at least from a human being comprehension aspect. The Borklet, Kubelet, so there are a lot of commonalities around that. So where does the persistency thing come from? So containers storage is ephemeral. That basically means that if the container is gone, your data is gone. And this doesn't have to be a problem. So if you're having a web server, it just serves out something from somewhere else. So it's okay if you lose that state. But it also means that it could be such that the data could be regenerated. So if you have a huge compile farm, let's say, and you're compiling code, you can regenerate the data. So you don't really care about the intermediate object files that get compiled by the compiler. In the case of serverless, which is also a very interesting thing to look into, is that you may have this intermediate state between the functions that you have, right? So the function is not just one function, could be multiple functions, and you need to figure out a way how you could actually share the intermediate states of these functions. So persistency is something that is important if you want to run these type of applications in a Kubernetes native environment. So containers need to persist, but while doing so, we would like to have the abstraction, similar to what we do with compute, apply to storage, right? So decouple the actual data. So having that said, the bar in terms of expectations that people have has been set by the cloud provider. So if you use an EBS volume in AWS or a persistent disk in Google Cloud, it comes with a certain, you don't have to worry or you don't have to care feeling around that. And it should be such that you can get that on-prem or whatever you want to run it. So let's look a little bit in terms of how that looks. So you basically have your pod spec, let's say, and then you basically say, I want to have a volume, and this is the mount point, right? If you do this, you will probably lose your data, because what you do then is it's confined to the host. And Kubernetes, at any given time, will reschedule your workload to some other node, and it won't not only move your data, but the data is actually gone. You just lost it, right? So you need to be careful with that. So probably a better way then, I suppose, is to use a cloud disk, right? Whichever vendor it is. And I took this from the Kubernetes site, so they use a GCE persistent disk. And the advantage here is that the disk is decoupled from the actual node that runs your workload. So if the node goes away or dies or whatever, that disk is still there somewhere, right? So if you evaluate, let's say, the options that you have, in both cases, we still have a problem because we more or less created pets from our herds. That's, I suppose, a popular thing to say. And they say, oh, you shouldn't do that, it's anti-pattern and yada, yada. That's all true, but it's not necessarily the wrong thing to do. But if you want generic storage for your Kubernetes cluster, it's probably not the best thing that you can do. And the second example, where we had the Google persistent disk, it was a lot better. But OK, so who mounts the thing actually when I move to the other host? Who does that? Should I log into the machine, mount it, and then go back to my YAML and move on? So there were still a lot of action, still a lot of questions that needed to be answered. So it was good, but still not great. So through community efforts, a lot of stuff has happened. They talked about persistent volumes and persistent volume claims, and the CSI initiative basically allowed for creating plugins such that every vendor could implement the CSI spec, and it would just work on any storage system. And the other reason, I guess there are two sides to the blade here, is that the Kubernetes repo did not contain vendor-specific code to work with Kubernetes. So they basically created this abstraction. So what's this PVC thing? So now you actually need to do a little bit more YAML, and we can talk about if that's a good thing or not. But so you basically create a persistent volume, and you basically specify on how that thing should look. There's also this thing called storage class. You can forget about that right now. But this is basically what you need to do. And then once you have created this persistent volume, then you can claim this thing, right? And once you have created the claim, you can refer to it into your application. And so it's basically a three-stage rocket, and then you finally have your persistent volume attached to your pod. So, it's to summarize it a little bit in more, let's say, common terms, is when the PVs are basically a pool of mountable things that you register to your cluster, and then you can actually put a claim on it and then reference it in your app, and off you go. The problem there is that I need to make sure that the storage admin keeps an eye on the number of PVs that have been deployed on the cluster, and if it starts to dry up, he proactively fills up. So it's like keeping a magazine of these things ready for action. So a dynamic provisioner allows you to actually have your CSI driver then, let's say, talk to your whatever storage system you have to dynamically create these logical units, and that makes things a lot easier. And then in the CSI agent, which runs on the node itself, there are the vendor-specific things to actually mount the thing to the host. So that's a lot of text. So let's see how that looks in a picture. So if you have two nodes, let's say, and I create this persistent volume claim, the trick now needs to be, what now needs to happen is that somehow, some way, the thing gets attached to the node. So you have your pod, and then I basically connect it to the host, but now comes the trick. I need to actually move that thing into the pod, and this is called, we just saw how that all works with mount points and namespaces and what have you. So we need to propagate, as they say, the mount into the pod. And then if we want to move the workload, we just do the same thing on a different node, right? So the data moves along. So that looks good, but I'm not sure where I am right now. OK, so that looks good, but is the problem solved? Because if I go back, no, oops, sorry. Yeah, this is a little bit hard for me. I figured out animation, so there you go. So the PVC here becomes like, how to say, it becomes a very important thing here, right, for your application. So if you lose it, everything goes to waste. So it is important where you put this PVC on and how do you manage this PVC, and would you, as a DevOps developer, care about how this PVC is managed? And that's what I meant with the bar is set by the cloud providers. There you don't care. It's just magically everywhere. But that doesn't necessarily have to be the case when you go on-prem. So is the problem solved? So what if you, as a developer, want to do specific things, or you know that there are specific things not needed, like example for encryption, replication, compression, snapshots, and clones? How do you do that in terms of YAML? So the CSI spec is actually working on these snapshot things, but there are some other problems still there, is that if you have different storage systems, and companies sometimes have different storage controllers and different data centers and whatnot, how do you converge the differences in their approach? And the storage efficient replication models are usually not interchangeable, right? I mean, they go out of their way to be completely incompatible with one another. So how do you make your data available like EBS style? So the other thing is that you need to abstract protocol. So if I move from a node that has a fiber channel, if people still use that, and I move it to a node that doesn't, right? Okay, now what? So I used to connect through fiber, but this node doesn't have a fiber channel card. Now I can't, attach my PVC. So you need to abstract all these things, right? So how do you do that? The PV and the PVC concept in the CSI driver doesn't actually help you there. So, and the other thing is, okay, so how do we reuse our existing storage then to create EBS type-like volumes in the behavior that we like? Last year, Google announced, and Amazon also announced, that they are actually going to, if you're not coming to the cloud, they'll come to you. So what that basically means is you can actually run GKE on-prem, and then you have all the good things of GKE on-prem, but not the storage, right? So how do we solve that problem? So the trick here is that you need to make your data as agile as the applications that they serve. And if you look back at the PVC that we just had, it's not just one PVC, right? You have, well, maybe 1,000 of them, right? So how does that work? So what's the problem there? So this is the concept of data gravity. And data gravity, and as data grows, you'll see that every application starts to evolve around the data. And there's a problem because these storage systems, they can only go so far. And even if they're distributed, there are a lot of ifs, ands, or buts in certain cases. So the other thing is the I/O blender aspect. You lose visibility the minute that it goes into this black box. So, and obviously the biggest problem, if the sun goes supernova, all the planets around it are gone, right? Instantly. They never know what happened. So some say, well, okay, so then we just set up replication and you buy another storage controller of the same vendor because you can't interchange the data, and you start replicating the data. And this works, to be fair, but it's not very granular, and it actually makes the problem worse. So to keep a little bit within the Star Trek theme here, that's, can we do better, right? And so we asked ourselves the question if that, what if you run your storage subsystem actually in containers and make them cloud native and use the same design principles that these personas use? And I have to attribute this to our CEO, who's very adamant. Before we wrote the first line of code, is let's talk to these people that actually do this, because we've built storage before, actually with him as well. So let's make sure that we get it right, because what storage developers typically do is they reason from the bottom up. So they have this disk, and now I have some couple of IOPS and some bandwidth, and that's like my holy playground, and I'll define how you consume it at the top, right? So we inverted that. So we talked to a lot of people, and the most probably important question is, what does it actually mean, right? The cloud-native architecture, and maybe this was really clear for you, but at least it wasn't for me. Getting my head out of my keyboard a little bit. So, but one thing that I noticed, and there are more things that I could put it on here, but time is only limited, is that the applications have changed and somebody forgot to tell storage. And what I mean with that is that the cloud-native applications are distributed systems by themselves, right? So things are built in terms of scalability. Things are built in terms of redundancy, and not only between nodes, but actually DCs and regions and even cloud providers. So if that is true, what does that mean for the complexity that you need to engineer inside of your storage system? So to make a comparison, if you have the traditional, can you imagine that I'm actually calling that traditional, but if you had a typical data center, you have VMware, and it had or something else, a mount point through whatever protocol, and you just put your application in there with an operating system, and if the node died, ESX would spin up somewhere else, and all is great. But the storage really became critical, right? because if the storage died, then everything died. So you really want to avoid that. So looking at the storage aspect of these cloud-native architectures, you'll see that, or what we saw and what we actually see in the data, because we have a lot of users actually trying that out, is that the individual data sets of the containers are relatively small, right? So instead of having a 1 petabyte volume, you had a lot of them like really, really, really small. And so what can you do smartly now that you know that that's the case, right? The other thing that we saw is that the notion of grabbing a thing and sticking it into your architecture became very easy to do with cloud-native languages like Ballerina and Metaparticle, and there are a couple of others. But not just that, concurrency primitives are getting built into the language to make, probably nobody ever types pthread create anymore. You just do something with an arrow in Go, for example. So things change a lot in the way that these software things are built. But there was more, obviously. So there's also the hardware side of things, right? Hardware is progressing. So we have 40 gig Ethernet moving towards 100. People talking about RDMA, NVMe, and NVMe over Fabric, which is a protocol. And the increasing core count, right? So how do we make sure that we actually use the cores that are available to us? And your application from 20 years ago will definitely not be able to consume that hardware to its full potential. And another thing that we saw is that storage limitations bubble up in the software design. So that's not to say that it determines how you write your for loop or your while loop or whatever. But if you look in the infrastructure as code aspect of it, it definitely does, because the things that the storage system does when it does its thing might impact actually what you can do from an infrastructure level. So, for example, if you are running a backup, well, let's not do CI/CD at that point, because we would back up all the CI/CD artifacts that we typically don't want to back up. And there was, because of that, there was a lot of friction between the teams, or at least that's what we experienced. They call that shadow IT. So the guys are like, okay, whatever, man, I'll just go to Amazon, put in my credit card. I won't wait for you to get me that LUN, in 2 weeks, because that's typically how it went. And then, when the biggest problem then comes when you actually want to move the application that you developed and demoed to everybody back into the data center, because now you have used these cloud-native patterns, and then you figure out, hey, my existing infrastructure can actually handle that. And one of the coolest things, or coolest, but it was shocking to me in the sense that there was this guy who had the budget, and he did, to buy every storage system in the world and just play with it, right? And it's like, wow, you have a cool job, man. But anyway, but at the end of the day, he said, I'm just done with all these idiosyncrasies of all these weird vendors. With this one, you can't do this. With this one, you can't do that. So if somebody needs a box, I'll just give them free, put an NVMe device in there, and say, you make sure that you replicate your data, right? Okay, so what does that mean, right? So a lot of small stars instead of a big sun that can go supernova. So and the enterprise features, you didn't care about that. The developer is in charge. The developer knows best what the application needs, and therefore the developer needs to make sure that the data is safe and all these type of things. So it seems like stateful workloads, storage, seems to be like an agile anti-pattern here. So doesn't look really good. So a little bit more about the hardware trends. So at the top, you can see a server. It's from Supermicro, by the way, and I was at SDC last year, and they demoed this box. And this machine, from memory, I think it has like 36 cores or something, and it has 1 petabyte of NVMe storage in there. It's like insane, right? A lot of people could probably condense their whole data center into this box. So no? Okay, well, my home data center at least would fit in. So anyway, and if you look at the CPU trends, which is very interesting, I think we all know that somehow, some way, but seeing it in graphs always speaks to the imagination. You can see that the red line is the performance is starting to cap, and the number of cores is going up, right? So if the clock frequency doesn't increase, it means that the CPU's capability of executing instructions is not getting any faster. It can only go parallel. So with NVMe, what they do is actually because then we're talking about storage that's actually straight onto the PCI bus. So how do you get all this performance out of the NVMe device, right? Because each drive in there can do around 1 million IOPS, right? And that's just an insane amount. And the key thing here, the takeaway here, is that to actually leverage these capabilities, you need to change your software architecture, right? It just doesn't work. So the final thing that changed was actually the people. And these people, they are responsible for everything, right? They have to, some companies actually have to figure out the requirements, then they have to build it, then they have to test it, then they have to put it in production, and and they also have to support it. So it is only fair for them to have control over this virtual infrastructure, right? I mean, you can't say, well, you're responsible for that, but I'll handle the storage or I'll handle networking. So you need to make them autonomous. So as I mentioned, storage hasn't changed at all, right? It's still big boxes, even software boxes, still boxes. So the idea that we had is that, okay, so on the right side, you have traditional stateless workloads. So what if we actually follow that model and I'm not sure if it's moving because yeah, I think it does. So do you have the same model? You still have your YAML, you still have your DevOps persona, and then when he spins up the workload, next to actually spinning up the workload, you spin up a container that handles the persistency of the data. Now, I won't go into great detail in exactly how we do that, but I'll give some examples later on. But if you happen to be in FOSDEM, I'll go over the bits and bytes and things like that. So when we thought, okay, so that might actually be a good idea, we imposed some design constraints upon ourselves because one of the things that we betted, I think that's 2 years ago, we betted basically on Kubernetes, and it was not all that apparent that they would win the war, let's say, but it turned out to be a good bet. But one thing that we did not do is we decided not to build another distributed scale-out storage system because 2 reasons. There were so many of them. But small is the new big, right? We could see small data sets. And so why would you build a distributed system? Because typically distributed systems are distributed because A, the performance, or B, they have high capacity. So performance from an NVMe device, 1 million IOPS, I got you covered, right? You can put 2 in them and you get 2 million. So it wasn't really needed. But the other thing is that if you have your application, which is a distributed system, and you have your storage, which is a distributed system, that's an operational nightmare, man. That's just like a disaster waiting to happen. So you really don't want to get into that as a DevOps persona, right? Not to say that distributed storage does not have its place anymore, but we did not feel that that was the right fit or impose this complexity onto the developer. We wanted to make it per workload, so each developer could define, doesn't have to, but can define exactly what he or she wants. Runs in containers, and therefore 4 containers. And it runs in user space. And this is a very interesting topic. It actually came very timely because you guys probably remember this whole Spectre and Meltdown whoopsie from Intel. It has its ramifications, and they are still getting bigger and bigger and bigger. They're trying to clean up the mess in the kernels, but the performance implications are considerably high. So that made our job even harder because if you're in user space, you need to do a lot of communication with the kernel, and if that takes more time, performance goes down the drain. So where do my million IOPS go if I can't squeeze them out? So, the other thing is we want to make the volume omnipresent, and I really like that word, by the way. Just for reference. But obviously, I don't mean that I would want the volume to be everywhere, but what I want is that I want you to tell me where the volume should be, and we will make sure that the volume is there, right? So if you're a DevOps developer and you have like 3 locations, you say, I want one there, and one there, and with one, I mean a replica, right? So you get to decide. And you can actually dynamically increase it and decrease it, but that's, almost obvious. Are we a distributed system or not? I typically say that we're not a cluster storage instance, rather a cluster of storage instances. So we have a lot of small storage systems running in your Kubernetes cluster. So instead of having a big sun, we have small stars, and Captain Picard likes that a lot better, I suppose. So. Another way to put it, if you look at, in a more traditional sense, okay, so what does that mean? So we have the SAN, NAS, and we had this guy who liked direct attached storage, DAS, and so we came up with something else. We called it CAS, and that's container attached storage, right? So, okay, so let's get into a little bit what that looks like. So, as I mentioned, so it's actually using Kubernetes to instantiate itself, right? So you define your YAML, and it follows the PV/PVC spec. We do all the magic in the background. And you can see, hopefully, that at a certain point, we go to the Kube API server, and there we basically implode the PV/PVC to a set of containers that we need to spin up. And the big difference here is that unlike the CSI plugin, let's say, we are not talking to an existing storage system, right? We're actually spinning up the services. Obviously, you need storage, but even if you try hard, it's hard to find a node without storage one way or the other. Yeah, so there's a lot more to it than that, obviously, but I can't keep on going, but that's roughly it. So the interesting thing, though, is that the number of containers then dramatically explodes a little bit. So we have worked with the guys from WeaveScope on this, and that's, is it moving? Yeah, okay, so, yeah, I can't see that here, so. What you see there is that we extended the functionality a bit to actually show you the relationship between the containers and the actual persistent volume, which is a container, right? So visibility is important. People can see in a picture a lot more than in 10,000 log files, right? So the other thing that I mentioned is, okay, storage as Agile as the applications that they serve. Okay, so that sounds kind of cool, but what does it mean? So a very simple example, if you ever upgraded a storage system, it typically goes like this. Okay, we need to upgrade the firmware. Okay, everybody schedule, clear his agenda, and we're going to do it on some weird day that nobody is working. And then somebody has to actually press failover to the other node, and everybody squeezes their butts because, it might go wrong, right? Because you don't do that all the time. So that's not really DevOps, right? So you want to switch out components of your storage system just like you do that every day. So the idea of blue-green deployment, let's say, is that I have this controller that I need to upgrade, and you basically swap out the controller. You keep the old one dangling, right? So if it's not working, you can swap it back, right? And that is, to us, is something that currently is not possible. So composable storage. Okay, so what does that mean, right? So we have this persistent volume, and then sorry, but I like this one. In Kubernetes, they changed the nomenclature from input-output to ingress and egress. So we have an input thing, we have an output thing, right? And then we have these devices underneath, whatever they are. They could be local, and with local I mean actually physically locally to your box, but they could also be local, in the same data center using some iSCSI protocol, or they can be remote. And then you want to have certain features, so we allow you to add certain layers that you need or not. You decide, you know your application best, like compression, encryption, and mirroring. And oh, by the way, it's best to do it in this order, so don't first encrypt and then compress. You'll be not happy with your compression results. But so that's at a high level the gist of it. So okay, so what does this egress then mean? Because if I have my PV and I'm connected to my container attached storage thing, so now what, right? How do I connect? Because as we saw, we actually need to connect this thing to the host and then propagate the mount into the container. So the way that we do that, and there was a little bit of work involved there, but we basically support all, well, not all, but mostly all storage protocols known to man right now. So network block device, NVMe over Fabric, TCP, iSCSI, and VirtIO family. So VirtIO is a protocol used in the hypervisor space. Because why is this important? If you look at things like Firecracker, Clear Containers, Kata containers, and what have you, is they basically strip down the hypervisor to a bare minimum to achieve security in containers. Because the containers are not all that secure right now, and even if they are secure, you can just start a container with privilege mode, and you have God power. So with these hypervisors, you can actually really create security. So we felt and still feel that that's going to be an important aspect of running Kubernetes in production. And you can see that these VMs use virt.io because it's the most efficient way to communicate with the host. Okay, so now we have an inbound way, and we basically need to do the same for the outbound. And so I could compose, as an example, so I choose as my input protocol RDMA, and then I write out to Gluster, AIO, and an NVMe device. I'm not saying that this is very smart to do, but it just shows you the possibilities. So being in storage, you probably know that you just don't go out and build a new storage system. And actually, I just noticed it. I've been using this thing for a while now. There's a typo in it. But anyway, so we needed to test this thing. And so how do we do that? One of the things, and we actually presented this at KubeCon, I think it was 2017, is that we need a way that we can do chaos engineering, because that was cool. So we created this E2E test system called Litmus, and I hope this works. I tried it several times here. The Wi-Fi is, I won't say bad, but sometimes it's not there. So I'm not going to click on it, but I put the URL there. You can go to this website. It's openebs.ci, and there we run our CI systems and run workloads, and then you can inject chaos into the workload and shoot a replica, and then it should rebuild, right? And then you can kill a target, and then a new one should be created. And this instantiation of new replicas and whatever, that is orchestrated through Kubernetes. So we are leveraging Kubernetes for that. There are some problems that we still need to solve, because sometimes the scheduler goes out for a picnic and comes back and oh, pot died, hold on. And then, it's probably already too late, but, we'll get to that later. So what does it mean in terms of CI/CD and what are we working on? So one of the obvious things which is important is performance. So we have our CAS container there, and we have this tool that speaks all these protocols, and we basically start to hammer it with all types of different protocols and different workloads, and then we see if it can keep up. So obviously, if you have a very busy system, the queue starts to fill up, and then you get I/O timeouts. And so where are we reaching this limit, and what can we do? What can we learn from it and improve? But the cool thing here is that instead of setting these things up statically, we can use the Kubernetes auto-scale system to scale up the workloads and scale them down, and actually make them, like a really, really sad thing for the container itself. So, and then we record these results, and we know how many workloads, we record the results, and if there is a regression, we automatically report that. And so these regressions can happen in these layers that we add, right? So we add encryption, and then we think about, we're even smarter than the rest of the world, so we have this new algorithm, and it turns out performance went down the drain. So this allows us to measure the performance, and this utility is just hammering and just doing nothing else but doing I/O. The cool thing is, though, is that the performance container doesn't need anything from the operating system, right? So you don't need a fiber channel card. Well, obviously, if you want to do fiber channel, but other than that, it doesn't need anything from the kernel in particular. It's completely independent. It's completely in user space. And the reason why that is important is that if you move your workloads from cloud to cloud, you'll find that every cloud vendor has its own image, right? So there's a problem, because not only that, they have their own images, they actually have their own kernels. And so if you write this kernel module and you want to load it into, let's say, GKE, it will probably not work. And even if it would work and you call Google that something's wrong, they will say, well, you tainted the kernel. I'm not going to help you. Good luck with that. So doing this in user space is important, really, really important. And that we, in certain cases, actually outperform the kernel was a bonus, but certainly not a goal. So we also use GitLab. Actually, the OpenEBS CI website is making use of GitLab, and we use these tags for those runners to say, there's RDMA here, and there's there, and this is that, and yada yada. But the most important thing is that first we need to pass the smoke test, which is this cast performance tool. If that doesn't pass, we fail the pipeline. And then what we also wanted to do is we really wanted to make storage application domain specific. Right, so storage system, typically, they have this Excel sheet or a data sheet that says, it can do this many IOPS, right? And okay, so that's good. That sounds like a lot. I'll probably buy it. But what does it actually do for your application? So how do we know how many Mongo instances you could run on a container with these dimensions? So we try to actually run real workloads. And you can imagine that that's pretty expensive because MongoDB needs a little bit of memory to work, and CPU threads, and all these type of things. So what we do is we actually record at the block layer the I/O profile of these databases, and we store this information. And this is a feature that is available in just Linux. Is nothing that we did. So we record its workload, and then we use FIO to actually replay that workload. And the beauty is that we can then again scale the workload, so now we have, 100 MongoDB instances, and so Cassandra does its compaction, right? So we can simulate exactly that Cassandra is doing compaction, and that's how we can, provide you information which ties back into the first slide with the analytics and stuff then. So we can actually provide some value other than providing you with sheer speed. The other thing is then that we use this litmus framework to inject all kinds of errors into this cast container that normally would only happen when you have hardware errors. So things like transient errors are like the worst, right? So you want to have your disk die or not just half dead, right? And typically they tend to do that. And that increases latency spikes, and you can't see it, and you see all these weird scuzzy things in your D message, and you can't make heads or tails of it. But so we actually can simulate these errors, and by capturing the logs, we can actually learn what type of failure impacts the workload, or in particular the workload, right? So if it is a particular error that happens still on the device, but Mongo doesn't care about this type of error because from a performance envelope, it's still there, we basically don't do anything. But if we can see that you guys are getting errors from a particular condition and you're running Postgres, for example, we can actually provide, or in the future, autonomously move this data set away from that node because it's experiencing errors. So the whole scheduling aspect of it comes back into play, and then you kind of have what Kubernetes does for compute, we do for storage. But then there is more. We want to make that automated, and that's where the Lambda functions come in, because it doesn't necessarily mean that that in your case you actually want that to happen. So give some room of programmability in terms of how you want this error to be handled, and the heuristics of what is an error. We actually don't know yet how to do that in the sense of providing a meaningful way, because if you have a disk that does 1 million IOPS and every day it has just one error, okay, that's fine, but maybe 10 in 10 minutes is not fine, right? Okay, so where's the balance? So we're still trying to correlate that information. So long story short, our goal is that just storage just fades away as a concern, and with that, I'm actually spot on, or at least for me. If there are any questions, please feel free to ask them.